Now it's recording. See, I'm fine. Okay. All right. So let's do this. I'm going to write down the definition um, of what is it? The definition of the limit. So here is our function f. It takes x values. And the question is, as do the nearby values to c. You see that? When I wrote this, this means I am only interested in nearby values of c. How do we say that the x values that I'm concerned about on the horizontal axis, x-axis, are nearby c? How do we say that in mathematics? We have to use some Greek. And we say that we are only concerned. What are the nearby or close values to c? The ones that are, yes, Russell? Delta distance. I don't have the brothers today, so I don't know where the hell they are. Okay, so if x is delta distance from c, then those are the x's that we are concerned about. So if we have a function f that takes x values, specifically x's that are within delta distance of the center point c, the graph should pop up in your head. Then the x values, the function maps these x values into functional values that approach a number which is not necessarily defined by the function, but is called the limit, L. Yes? Okay, so if we were looking at this definition intuitively, this notation that says that this function has a limit L, we would say as x goes to c, f of x values approach L, or we could do better than that. We could write this as we are only concerned about all the x's that are nearby c. This is too much. This could be all the way from Karachi. So we go c minus delta, c plus delta, all the x's in this is in a get mapped by the function f into functional values that end up in this open interval, which is on the vertical axis. So we'll have L minus delta, epsilon, L plus epsilon. And do you see how when we were doing sequences, we were using epsilon on the vertical axis because the sequences is also a function that takes a natural number and gets us, and the functional value is then put on the x-axis. And so we use the epsilons on the x-axis. Now that we have two vertices, epsilon goes to where the mapped values of the x show up, of the function show up. So that's why epsilon ends up on the vertical axis and delta is down here. We have to bring a delta in. Okay, what's a better way to, or what is the harder way to say that we only want to talk about x's that fall in this? So we say this function f has a limit L if all the x's that are defined within the delta distance, within delta distance of the center point C, and not necessarily the value of C itself. So we do that so that x is never equal to 0. If you subtract that, it should be greater than 0. Otherwise, if it is equal, then these two numbers are equal. So this is saying what? We are only concerned about x's that fall in this. let's draw the picture here. Who the hell did these lines? Huh. Okay, so we're down here. Here's our function. These are the x's that concern us, not this guy, and not this one. So we are only interested in the x's that are near, close to C. How do you say that in mathematics? You bring in a very small positive number to show that. You go, all the x's within delta distance of the center point C, and if they're defined, when they get mapped by the function f, then all the functional values, if they do end up being only epsilon distance from the limit L, then this function f has a limit L. And so let's go right here. Oh, do this. So if all these x's get mapped to functional values that are close to this one, which could be defined or not, in this case it's not defined, because this x should not get us a value here. This x should not get us a value here. These x's should only hit the nearby parts, near L. So then this would be L plus epsilon, L minus epsilon. If these go and hit between these two guys, if this x goes here, ends up here, these are fx. If every x in this open interval, or every x within delta distance of C maps into functional values that are also are always and without exception within epsilon distance of L, then this function has a limit. Okay, it cannot get clearer than this. So I think. Russell, what do you think as a STEMmer? Where are you still fuzzy somewhere, or do you see the bridge between the intuitive and the rigorous? You're still unhappy. Hmm. Right, and that will do just now. Okay. Sophia, question, as a STEM person, how you feeling? Yeah, okay. Anybody else? Lauren, you're good? Okay, excuse me. And that we will see, okay, so to that question, let's do that. So what happens is that to prove that a function has a limit using this definition, first thing we have to do is find the proper relationship between epsilon and delta. And there's usually some integral whole number relationship. So for instance, if epsilon equals 1, let's say we want from L, all the fx values need to be one distance, then maybe the delta needs to be half of epsilon. So what happens is what is given to us is not this. What is given to us is the epsilon. We're never given this, even though the definition goes from this side to this side. So what happens is first thing you have to do to prove that a function has a limit using this definition is something called doing scratch work. Scratch work involves figuring out, given any, right? Because this has to be any, for any value. For any value, what kind of a thing do we need to multiply that so that we get the right sized delta? Once we have done that, then we just apply this definition in this order. Okay, and so this is the hardest part of the proofs. Given a function, first thing we have to figure out is for any sized epsilon, what is the proper multiple that goes here that will multiply into the epsilon to give us the right sized delta. In my PowerPoints, what I've done is I'm saying where the graph meets the horizontal lines, that's where you draw the vertical lines. And that gives you the right size of the delta. So we'll do that in a second, okay? So, so this is scratch work. Once we figure out what is their relationship, then we go and use this definition. And so we start here and make this look like that, right? Because this is what? And if then, remember the theorems we were doing for the last 2 months? So there you go. So that's how. This scratch work is the confusing part. And, but that's how, once you've done that, then you can go there. And the problem is, this is what's given to us. Because this is, and you can assume any number for that. And then there has to be a delta that works. And how do we figure that out? We need this guy. So this could be 100, this could be 45, this could be 70. If we have the right whole number here or fraction here, it will get us the delta that will work with whatever we put in. Okay, so let's make that a little bit more concrete, or actually not concrete, but we'll just do the pictures here. Okay. For concrete, you're welcome to look at calculus textbooks with actual examples, which I had to do for my poor daughter who was going to Fairview. That's when I really got into this. I'm like, what the? They don't even do it in college here, and they were doing it at Fairview. Barely scraped through with a B. Crazy teacher. Okay, so let's write this down again. We have this means, how do we expand this? If you're given this, we can then expand this into an equivalent statement. And the equivalent statement says if that this exists, if, what exists here, if and correct me if I make a mistake, then okay, so all right, so how do we show it pictorially? And how are we doing on? We are not doing well on time. Shit. But at least you guys are getting it, right? That is probably more important. Because time is what we have in this class. And time is what actual professors of mathematics don't have in their classrooms. They have all that material to go through. Okay, so right now, what do we have? In this line here, what is actually given to us? We're given the function, okay? So let's draw the function. Our function is going to look like this. It's a decreasing function. Okay, here's our function. What else do we have? Do we have the center point that we're interested in? Yes, we have C. So I can stick that here. Do we have delta? We don't. Because the value of delta depends on this, because this can be any. So what we have is we have 500 million sized, we have one, we have half, we have a very small. This is the given thing. So we have, if we look at this definition here, this thing expanded. If this is true, if we have this and and this lets us say this, then the limit exists of the function. So at this point we have C, we have a bunch of x's, but we don't know what the value of delta is because we have to figure that out. So right now we just have, so we can give this any value. So I'm going to, oh yeah, we We have L that we don't know is a limit or not. So that is still a question. So at this point, we don't know that as x's go from right and left towards C, or the nearby x's map into functional values that end up nearby L or not. We have L, we have C, and that's it from this definition. So our first job is to calculate the delta. And to do that is we can assume the epsilon. Let's assume it to be this big here. So this is our epsilon. So how long is the epsilon? It's this width here, right? Okay. Now, next step is draw the horizontal lines. All right, we're looking good. Now, what we want to make sure that once we've figured this out, all these fx's fall within this, right? So now, what is the value of delta? How do we figure that out? From the graph, the trick is draw vertical lines where the function, this curve, intersects the horizontal lines for L plus epsilon and L minus 1. So this right here, it cuts here, and it cuts here. If I draw vertical lines here, these vertical lines will determine the size of the delta. So it looks kind of off, but let's pretend it's the same size. Oh, actually, I can move this guy here. Okay. So what is, excuse me. If you have this sized epsilon, what is the size of delta? Let's say if epsilon equals 1, I think the delta is half the size. Looks like it, right? Or is it the double? Is it double epsilon or is it half the epsilon? Which one should we go for? Oh, I know. I can do it. Or they're equal too. You know, when are they equal with this curve? So, so let's forget about that because the picture sucks. 1 second. It does look bigger. So let's do a double. So what we have just done is we have determined the value of delta by just looking at a picture rather than actually doing it mathematically, which I recommend by going to the textbooks. Okay, so we're looking good. Now the question is, we have figured out our delta by drawing vertical lines where the graph, where the function cuts these horizontal lines. So our interest is in this box. This is the box we get. And this box says only these values of the function matter. So now let's just check at least one. Does this x map into an fx value that falls into this open interval? Let's see. X goes, oh, it's in it. And bam, right here. Let's try another one. Bam. Looks like every x maps into a functional value that falls within epsilon distance of L. Okay, so Sophia, how good is this? This is still solid? Okay, all right. If only my math teacher was like this. But again, they don't have time. I don't blame them. You guys are supposed to spend the time figuring it out at night. but nights are for owls. Okay, so the problem is we just randomly picked an epsilon. What we need to do is keep changing the value of epsilon and seeing if we can figure out a delta that works. And that's the whole thing. And if each time we change the value of epsilon, we can figure out a delta, and then all the fx values fall within epsilon distance of L, then L is the limit of the function. So let's go for it. I think I'll just use, I'll make it, if I make it bigger, it will work. If I make it smaller, let's see. What if I made it smaller? So I'm going to erase this. So now our new epsilon is going to be smaller. And it is represented by this solid line. So this is our new horizontal line because the epsilon is smaller. This was our old one. So now our, excuse me, we have 6 minutes. Okay, it's not bad. So we have this. Oh, no, we used to have that. Now we have this. This is our smaller epsilon. And smaller epsilon here. Can we figure out a delta now, which gives us x values that will map into there? And it looks like, and how do we figure out that delta value? Graphically, where the graph cuts the horizontal lines. We draw vertical lines, and that will give us, yep, that is true. I can see that this is the correct relationship because it is kind of double. So this will be our new C minus delta, and then this is our new, so this is our new smaller interval. And now every fx, every x maps, and this is the part of the graph that we are interested in. All of these fx's fall within the new epsilon value. And in fact, for this graph, you can try out every sized epsilon. You'll always find a delta. There are graphs, there are functions that don't, functions at certain points of the function, at certain points do not have a limit at that point. And then this process will fail for one value of epsilon. We won't be able to find a delta value. Okay. All right. So we got 4 minutes. Okay, let's look at two naughty cases quickly. Okay, the ones where things don't work out. Let's do the, where's my picture? Here we go. Okay. No, actually, I only have one case where it doesn't work. Okay. Also, you can also figure out the left-hand side and the right-hand side for this as well, where your center point, and then you only have when you have where your okay, what am I saying here? Let's do that. If we were to have this graph, this is okay. I'll just make it again. Okay, so we have. I'll just do one thing right now, maybe. And how was my graph? Here we go. So this is C. Oh, this is L. This is our L plus, L minus epsilon, and then C. If we are going to do the right-hand limit, then our interval is going to be C and C plus delta. You see that? So this side will be missing. And now we are only concerned about the x's to the right of the center point. does the graph from the right, all the x's nearby C from the right, do they end up getting into epsilon distance of L? And the answer is yes. Okay. And then the same thing will work for the the left hand limit. And so then this would be right here. C and then C minus. Okay, and then all of these guys, yes, do hit and fall within this distance. Excuse me. I think we should stop here. It's a fucking nightmare. But that's the thing. If you engage with slightly, this is the easy shit in mathematics. But not really, right? Because it never gets cleared up. What a disaster. All right, folks. So I'll see you guys Friday. We're going to finish this up. Quiz on Monday on this stuff. And then I'll make the quiz super short so we can start doing differentiation on Monday. Yeah. Should take a picture of that, but actually I have it here. So what do you think? Are you happy now, Russell?